Ah, there we go. It works better if I unmute. Hope you're all having a blazingly fun time. Let's see, quick check. I know Emily is there. Emily, are audio working? Hey, no. Okay, fine. So, actually, realizing that Emily is in both classes back to back, just when she mentioned that, barring any huge problems with people, I don't think I've ever had a real problem with moving an exam out one day. I think I originally had planned it for Wednesday, so I apologize if I've been stressing anybody for saying mentioning an exam for Monday. So yeah, I think it's going to. I think it'll work better. I've got a couple of things that I was actually concerning myself about as far as getting material on the pumping lemma and doing a couple of examples here. So you'll have the test is on Wednesday. I put in the announcement to that effect just moments ago when I realized it was going to be back to back. So with the algorithms. So the test is on Wednesday, so that'll give you a little extra time, and also I'll start recording it. So we'll do that here, and that'll give a little extra time, and also some opportunity to ask some more questions. I also posted a couple of things for you that I wanted to talk about. So overall, this is just going to unsquish our time in a technical sense. And we are recording. I think we are. Yes, we are recording. So to start with, let me point out. I'm just going to touch on the documents that I posted earlier. Hopefully, can get to. Okay, so you should be seeing our friend the pumping lemma. Okay, this is just a another walkthrough. Hopefully, what I would suggest, here's my recommendation, is that you read after last time we had a discussion. It was kind of somewhat restrained by the lack of video, but or lack of good whiteboard video. But if you take that plus reading through the book where it describes the pumping lemma, and then, this was intended, I wrote this as an add-on, as an explanation of those finer details to the pumping lemma. And then shortly here, just recap quickly the picture, the big idea from last time of it totally makes sense. The pumping lemma totally makes sense. Okay, as far as when you understand what it's really saying, and it's a little bit difficult to get there. Hopefully this will help you to understand that, what we said last time, and then I'll do a quick intuitive description of it here in a minute. And then we'll show how do you prove that a language is not regular. And it's actually, this is kind of a stumbling block for a lot of students, but it is a logical, it's a good logical exercise to see that taking a basic characteristic of regular languages and then showing that that basic characteristic cannot be applied to a non-regular language. And the logic involved there, that step of formulating the argument is something really good for you to take out of here. So we're not going to make it a huge number of points necessarily, but I would like you to exert some effort to get the pumping lemma down. There is also posted, and this is, I'm sharing the correct screen. This is a description of the process for converting an NFA to a DFA. Here is the algorithm that I did in class for you on the board. So this example includes a regular expression. This is using the plus sign instead of the union or the vertical bar. They all mean the same thing. So this is take a 0 or a 1, as many as you want, and you should be able to see the correspondence between this little section here, 0 plus 1 in parentheses star. That's 0 or 1 star. That's just Q0, right? We can take as many zeros or ones as we want, including 0 of them, followed by a required 1 0, and then followed by a required, there's no star after the 0 or 1, so you must take one or the other to fulfill this regular expression. And so this is the level of, if you see a regular expression like this, be able to turn it into a reasonable NFA or DFA, and given an NFA or DFA of this, no more than this complexity, be able to come up with the regular expression corresponding to that. But now these are the steps, and I wanted to do another NFA to DFA as an example. So we'll use this. You can follow along. And we'll and actually do a full example. And then the last thing was some sample questions. Okay, so oops, I should have taken out for the online exam. There'll be no drawings submitted. Well, we're not doing an online exam, so this is applicable to our in-person on paper exam. The point values are, this does not add up to 100, and give you a rough point. Typically, a true-false question will be 2 or 3 points in my exams. So these are the kind of true-false questions that I like to include. Should be true only if it's always true. Otherwise, this is the additional point for if it's false, then you should explain why. Put a little a note, not full sentences or paragraphs or anything, but mark why it would be false. Okay, we can touch on these. Every DFA is a specialized case of an NFA, true or false. Oops, let's see. I lost my meeting here. Do I have my meeting? Oh, if I go to the meeting page, then that's going to change. Yes, that is a true one. How about generally an NFA accepts a broader class of languages than a DFA can? Are you going to fall for that one? Oops, sorry, I'm switching. Trying to get back to the meeting. There we go. That is false. They are the same class, the regular languages. Complement of a regular language may or may not be a regular language. This is, oops, I keep missing the meeting button here. How about it? Complement of a regular language. Do you still have a regular language? That sounds like a good one to keep on the exam. Yeah, so actually this would be false, is the correct, if you reread it there. False is the right answer. Because it must be a regular language, as James said. So how do you know that? We have a quick proof. Another question, right? I could ask something, reformulate this and ask, can you show that the complement of a regular language is a regular language by an example? Well, from the homework, if you actually did the homework, one of the problems was to create the complement of a simple language. And so you just flip the accept states on a DFA. Doesn't work for an NFA, but for a DFA, you can flip the states and you get the complement of that language. When you turn accept states into non-accept states and non-accept into accept, then you get the complement of the language that you were dealing with originally. So yes, it must be a regular language, and so the question as formulated is false. You cannot say that it could be regular or might not be regular. It indeed must be regular. In order to accept an input string, be careful here. An NFA may ignore leftover characters in the input it is found if it has found a path to some final, excuse me, final or accepting state. Well, this is made to sound plausible. Is it true or false? Arman says false. Who will stand up with him? Yeah, it has to accept. Remember, the NFA has to use up all the input and reach a way to the accepting state both of those have to take place. And so, yeah, you can't just have characters left over. Now, it may fail. So the, just to be complete, it may not accept because it has no path to go on, and there'll be leftover input, but it can never accept and have not gone through all of the input. Okay. Let's see. We've just talked about what is a language. It's a set of strings that may be infinite or finite. Regular language is one that is accepted by a DFA or an NFA. Hey, what do you think? Can you show that this language is regular? How would you do it? Strings over 1, 0, ending in 0, 0. What do you think? Does that thing look regular? How could you show that that was regular? Yeah, there you go. It is regular. And the proof for that would be a simple DFA that you could also use an NFA. But the idea is you would, I think you'd need, let's see, ending in 0, 0. Yeah, actually, I think you need a fourth state to, wait, 1, 2. I think you need a fourth state for a null, a dead state, James. So I think it'll take you 4 nodes, but yeah, you would draw a DFA that accepts that language. We'll look at an example of a non-regular language here as well. Can you do it in 3? I'm just I think you need a, right, you need a 0, so you need one state to jump from 0, another state to jump into 0. Hang on, we'll draw it. But let me, I think we're almost done here, so I'll go back to my video after, let's see, is there, okay, draw a DFA to accept the following language, build the complement, describe in words or regular expressions a language accepted by the following 2 DFAs. I'll give you one. Some pictures to work off of. Build a DFA representing the union of those guys. If you do something like that, then it's going to be simple, couple of states. Difference between intersection and union, so building those. Build a DFA to represent that. Convert following NFA to a DFA. You will get, I don't remember, I remember that I mentioned, but I probably didn't write down, you will have one sided sheet of 8.5 by 11 paper to I'll throw some, I can throw some graphics at you. I have to, I don't remember what the graphics were on that. I can give you some possible examples, Armin. I think that's about it. Yeah, okay. So I think I'm done sharing my screen here. All right, so back to video, and that one question I wanted to strings over 1 0 ending in 0 0. There's my marker. And we, yes, are recording. Okay, so only strings that we will accept, and this is a DFA. To build this, we obviously are going to need something that'll loop on zeros and ones, so it's strings over the whole set. Ending in 0 0 means I have to go a 0 0. That'll get me to an accept state. Has to be the end, so we don't want to do anything from here. Oh, yeah, I guess I was thinking null state does not need to be here. If I have zeros, if it ends in 0 0, I can have as many zeros as I want. So that works. Now we just have to fill in. If I see a 1 here, I've broken the 0 0 pattern. So 1 there gets me back to start looking for 2 zeros next to each other. If I get 0 0, I don't care if I see more zeros, but if I see a 1, I have to go back to the drawing board, so to speak. I have to go back to there. And yes, the astute observation by James is that, or let's see. Yeah, agreed. Yes, go ahead.
This is a DFA. Would we still be able to have Q0 be able to also loop in at 0?
Oops. No. Nope, I jumped too fast. Thank you for pointing that out. So yes, you can only have one transition per symbol. And so any number ones, I'm happy. If I see a 0, a single 0, followed by a 1, it gets me back here. 2 zeros gets me to happy land, but then a 1 means that I did not end on 0 0, so I have to go back and crank through some more here. So this would be the final correct answer.
Let's say Q2, rather than the way you had Q2 when you have a 1, it goes to Q0. You had Q2 if it had a 1, it goes to a null state. Would that still be correct?
No.
No?
Because that would die on this input. So okay, so is this in this language? This should be accepted.
Yeah.
But if we went 1 0 0 and a 1 took me down to a null state.
Oh yeah.
It would kill it, and you'd never see those other 2 zeros. So that's part of the challenge of these things, is accepting what you should accept. And sometimes you have to look a little bit beyond kind of your first sense of when should we stop accepting.
Yeah.
That's always a challenge. So, yep. So it's good to, draw it, and then with your kind of intuitively draw yourself a variety. I mean, not draw, but you know, test your machine with a few different examples that you know are in there, and try to think of some, you know, the not obvious. You know, an obvious string, I guess I'd say, is 10100 or something like that. But something that has two groups of zeros, if that, then you might find a case that you missed along the way. Okay. All right, so I'll get some answers on those other. We went over the true falses. That's a bonus for people who actually look at the video or attended. So, all right. So we want to get back to that topic of the pumping lemma. So. We'll have the pumping lemma simply says that if you have a long enough string, and it is if you have a long enough string in the language, so it has to be it has to be able to be accepted. And it has some repeatable or pumpable right. So I think the I've taught this for a while. And every time, my little challenge is, can I come up with a, it takes you gotta work, you gotta do a little bit of work, but I have worked on this for a number of years, a number of classes. I've taught this course, let me think here. Probably 25 times at this point. And the pumping lemma is, I've used, there was another book that we used first, a long time ago, and it had the same kind of, this book is actually a better explanation. But there's something about, you know, the formality of trying to word it in the definition that seems to just be a stumbling block for people. And so I keep trying to come up with other ways of saying the same thing. So the underlying idea of the pumping lemma is this, and I'll draw a picture of machine to kind of hopefully illustrate it like live, like we did. Less, well, it was live last time, but I couldn't scratch and do things on it very easily on the piece of paper. So if we get this out there, I'm taking, kind of expanding on the idea of what's behind the pumping limit. It's really saying a simple thing that if you've got a 4-state, let me try this. Let me do it this way. If you have an n-state DFA, say any greater than n length string in the language must repeat a state. Okay, so does this make sense? Does this make logical sense? If you have an n state, let's just start with, let's start with 1. If I give you a, let's just say this is strings of zeros, from any number of zeros. It's like 0 star. And this is the accept state. If I feed it a string of length 1, have I repeated a state? If I give it a 0, then I was in Q0, I did a transition on 0, and guess where I am? I'm back in Q0. So I must have repeated a state in order to get this accepted string. Are you with me? Let's go. N is equal to 2. Here's another little happy DFA. What does it accept? Well, any strings over 0, 1, or 1, 0 that what end in a 0 and are at least have to be at least 2 characters long and end in 0. Right? So if I give, what is a string that's in the language is, well, 0, 0 is in here. Did I repeat a state? In other words, did I come back to a state that I saw before? There's only 2 states here. If I take a 0, 0, I came back to Q0, so yes, there's a repetition there. And the point being that if you, by the definition of what a pumpable, that means I can repeat some sequence as many times as I want. If there's one loop through the state machine, then it could accept a longer string that took it down half again, right? So remember, we also put on the little caveat that the language itself has to be infinite, because if you just had a strings of length 5, then you're not going to, that would just be 6 states going 0, 1, 0, 1, 0, 1, and ending at the 6th state, meaning you've consumed 5 characters, and then going into a dead state if you have more than 5. So you have to have exactly 5 characters. Well, that's a finite language, right? It's just all the combinations of zeros and ones that you can get and put into 5 characters. So like 2 to the 5th total number of strings, that's not infinite. All right, so here's the pop quiz of the day. Please respond to this if you agree. Typing quickly here. There we go. See if we can read that and respond. If you can go, I'm getting that, then we will press on, or I'll try to field some questions. So I just put in the chat I get that a string in the language of the DFA, in the language, longer than the number of states, must have some repetition happening, right? Oops, I forgot to find the mute on the responses. Excuse me. Okay, I've got a number of you on board here. Okay, I guess if you can formulate a question, if you're not on board here, or if you're snoozing, primering the Jeep while you're supposed to be listening to class, and you can pick this up later, then see if you can formulate a question. Why do you think this could possibly not be true? Can you formulate a if you can give me an example, if you think you have an example where the string could be longer and you're not repeating states and you couldn't keep making it longer, if you can find the counterexample in that is keeping you from buying into this, please speak up or forever hold your peace. We'll press on. So this is the foundation of the pumping lemma. Get a long enough string, then it's going to have to repeat some states. What that means practically is that there's some section of the strings in that language, right? It could accept various length strings. There's all kinds of different ones. But what we're saying is that if the string you feed it and the machine says yes, okay, so those two things have to be true. You feed it a string, and it is in the language. That means you end up using the input, and you end up in an accept state. And the language is infinite. Okay, got all those. But if that's true, if I can make a string longer than the number of states, it may be shorter. There may be repetition just on the first state, so I could feed it. The length required to repeat a state could be less than the number of states. I'm not saying that, but we're guaranteed that if we feed enough characters into the thing, if I know it has 6 states, to an accept state, if I can feed it anything more than 5 characters and end up in an accept state, then I know there's a loop somewhere in that machine to accept that. And I don't have to know what that is. I'm just calling it the letter P, the pumping length. It'll vary for every precise DFA that you have. For every instance of a DFA, it could vary, but we know that it cannot be, P can never be, it can be less than the number of states, but it can never be greater than the number of states. Why is that? Because the number of transitions is always one less than the number of states that I went through, right? I start in a state. If I go through 3 input characters, then I have to go to 3 more states from the state that I was in, or back into the same state, right? All right, so now we want to look at this. How do we apply this? We can't use it. If you read our friend the pumping lemma, I urge you to read that with on top of what we've just talked about here. And now what we want to look at is example in the book where he's actually going to prove that certain languages are not regular. They are languages that require some kind of counting in order to get an acceptable string in the language. Poor little DFAs and NFAs do not have any counting capability. Okay, they can only, let's say their ability to count is very extremely limited and dependent on using states. The only way you can count with a DFA is by transitioning between distinct states, right? If I let's illustrate that. Okay, I think we beat on this. If I say, write let's see if you can, maybe somebody's got JFlap ready to roll. Any Automata fans out there? Can you draw a DFA which will accept strings over, I'm going to do A, B, of length 3 2, or 1. So that means it does not accept what? The empty string. So here's just to build on. And then we're going to look at a not regular language. I laid my textbook down. Maybe I didn't get it out of the backpack. Well, maybe I was just reading it for pleasure before I went to bed or something. Okay. So, can you draw this? Hopefully you're making an attempt. Maybe just another couple of seconds. All right, strings over A, B, and we have to have length of exactly 3, 2, or 1. This is 3, 2, or 1. This is just a star. It's hard for me. I've got a little tiny 1" by 2" monitor here. Yeah, thank you, Emily. Okay. So, hey, this is this could be a valid kind of question for an exam. Yeah, it's interesting. One of the limitations of, let's see, I think I am spotlighted, but I cannot pin myself as the presenter. That would be the logical way if we had a user interface that would work logically. Let's see, I'm looking, I can spotlight, I can switch camera, and those are the only options. So actually an earlier, when we started this whole COVID extravaganza, I could actually make I actually had a bigger monitor, and I could see myself, and I could actually make it the size of my screen. La-di-da. Okay. Yeah, well, the nice thing about MS Teams is they have no constraints as far as trying to, prevent changes. So let me see what Nick came up with here. Yeah, that looks like exactly the thing. You can accept a 1 AB, length 1, a length 2, a length 3, but you try to feed it anything else, and it just goes into the null zone. Yes, so that is good. In case this isn't, let's see. I've had people claim that they could not see some of the graphic things if they try to go back in the recording. So I'm going to just whip it out here as an except for length 1, length 2, length 3, and then anything more than that, you get to the null, the dead state, right? So this is the solution to that. And so you notice that the only way it can count, it's not saying you have an arbitrary number, an example of a not regular language, I'll represent that here in a second, is having something like any number for the same number of b's. So we might represent that as a to the n, b to the n. That's supposed to be an n, not an h. All right. I will put up $500 to anyone who can write a DFA that will accept that language. I will give you an A for the course if you can make a DFA that will accept A to the N, B to the N. Wahaha. So you might be getting the idea that that might be either extremely difficult or downright impossible. Pick the second. It turns out the A to the N, B to the N is not a regular language. It kind of, on surface, you might initially think, well, it's just like any other, kind of looks regular-ish, but it turns out that the counting, yes, I should, or an A, Emily. I was negotiating there. I should have, I was incomplete in specifying this. I should say for n, say greater than or equal to, and I'll say greater than 1. So that would include A, B, B, A, B, B, B. ETC is not a literal, it's a language, an English abbreviation. Right, so that's what A to the N, B to the N would look like. So as soon as you draw it is not, unless you, what's the problem with this? Does this accept? I'm going to ask you a trick question. Have you ever considered owning your own business and making millions of dollars? I did. Come join my multi-level marketing organization. No, that was one trick question. Here's the other one. Oh, yeah, I'll give you the A and $500. Okay, so here's the trick, the real trick question. Will the DFA I have here except strings that are in A to the N, B to the N. Being very careful here. Here it is. OS. Ron jumped in with a yes. Okay, let me ask it this way. Will it accept 5 A's followed by 5 B's? That DFA? Now be careful. Yeah, so it will accept. Now, yes, there you go. Ron hit it. Emily. Right, and I'm not sure Emily's wording. Yeah, I have to loop on Q0, right, for 5 A's, and then go to Q1 and loop 4 more times on that. In my example here, I said for n greater than 1. Okay, so some of you picked up, right? What the problem with this DFA relative to A to the N, B to the N is that it cannot, I will say DFA cannot accept only strings in A to the N, B to the N. Right, so it accepts, it just so happens that A to the N, B to the N is a subset of the strings in this language. And what is this? What is this? What is the regular expression for this guy that I drew? This is a plus. Oops, no. Take it back. This is A star B plus. Plus, remembering star means 0 or more, plus means 1 or more. So this is the language of any number of A's, including no A's, followed by a B, and as many, at least one B, and then as many as you want. And that's all you get. So I want to say a to the n, b to the n is a subset of a star b plus. But a to the n, b to the n is not regular. Okay, so we've kind of shown by a lengthy way. I don't know if we've done a formal proof here that a to the n, b to the n is not regular. But we can use the pumping lemma to do so. And the argument will go like this. And I will give you I'll give you further guidance on what you should be able to do for the exam regarding the pumping lemma. I'll give you some sample kinds of questions. You will not have to do a formal detailed proof, but I may ask you to say, show just what I'm getting ready to show here. We've got about 12 minutes. We should be able to pack this one up. And it's going to do like this. According to the pumping lemma, what we're going to do, pumping lemma says that if you've got strings longer than the pumping length P, and I just showed you pumping length P has to be less than or equal to the number of states in the DFA, right? Up to in order to get strings that are both in the language and meet the repetition thing. So we'll say here n greater than 1. So we pick a string. So this is L. This is the language. All we have to do is pick a string in L. I'm going to pick A to the pumping lemma length, or pumping length, B to the pumping length. And I chose that on purpose. All I need to show show that there's no pumpable substring such that X, Y, I, Z is in L for I greater than 0. Okay, there are 3 possible cases here. if you look at it. The restraints are that let's see, this has to be in the language. Y is greater than, length of Y is greater than 0, so it has to be a not the empty string. And XY is less than the length of XY is less than the pumping length. So what are the possibilities? We have I missed some. Well, if we choose string as some part of just consisting of A's here, can I pick some number of A's? So we're choosing some XYZ string in the language. We're going to break it into 3 pieces. So this could be X, could be Y, and it's going to consist of 1 or more A's. And we're going to make some room. And Z can be the B to the P. Do you see a problem that will happen? I have P, quantity P of the A's. Okay. If this string is accepted in by a DFA, and you told me this is the pumping length, then there's some kind of a loop must have happened here, right? That's what I've been taking the last 2 class periods to get the intuitive feel that if you give it, if you only have P states at most, and you give it P characters, you had to have repeated one somewhere. So I'm telling you the pumping length is P for this machine, this now imaginary DFA. Pumping length is P, and I just said, okay, we'll just do for A to the N, B to the N. This is in the language, A to the P, whatever that pumping number is, followed by same number of B's, right? So what happened, is there any way that I can add within those first P characters? Here's my X and Y, and there are initially a total of P A's here. Or the length, so use vertical bars. The length of this is P. Can I add any, is there any way I can add A's within those first P characters and still have a string that's in the language? Well, no. If I add a single A, it makes the count go wrong. If I add 2 A's, it makes the count go wrong. There's no substring that I can make out of all this that I can just repeat that one or more A's, because the length of Y has to be greater than 0. I have to have at least one character, one symbol in there. So our argument simply goes, you cannot pump in A's and have a string in A to the N, B to the N. So the conclusion is A to the N, B to the N is not regular. And that's all the outcome from the pumping lemma. If it's regular, you must have some repeatable section. That's the nature of what the regular language can do. And so the pumping lemma says, well, if it's regular and it's long enough, you can add within those first P characters, right? This is totally making sense. We showed from DFAs that if you put in whatever the pumping length is, if you got and all we care about is long enough. We say P is whatever character makes it repeat without having to necessarily calculate that. And so the simple conclusion is, well, you can't just arbitrarily pump in characters within the first P number of symbols and have something that matches. And that's just underscoring that a DFA cannot count. It's not able to keep track of where it went before so that it can retrace those steps. What's another way to say it? It can only keep track of a finite number of characters by the number of states that it has. Like we did examples of, you could force it to have strings over A, B that are of length 3 only, right? We could have taken away some of those except states. But as soon as you say that, I mean, it really, you don't have an infinite language anymore. So DFAs cannot do math or count or tell where they've been previously. So I'll post a couple of other examples. Now hopefully you can trace through what the textbook has. I'll try to I'll list like 2 other examples and post them here in the next day. And then we'll have final questions and review next time based on your questions for the exam a week from today. And then finally, I will start on some new material that will not be on the exam. Yes, Arman, I will, I'll get those up there so you have those. So you got a little extra time. You'll have, we can ask questions on Monday. If you have questions while you're studying, feel free to email me. I'm less immediately responsive on the weekend, but I will be on the lookout since we've got the exam coming up next week. So I will be looking for any questions that you might have. All right, shutting down. Let's stop the recording and let me know if you have any questions about also the implementation of the DFA. If you have questions on that, get those to me sooner rather than later, please. Oh, thank you. Regarding the previous lectures, I'll make sure those are available through the team. Or, well, I think I can just post them in the team, in our class team. But if there's any problem, that's my default. I'll try to put it in the team. If not there, then I'll put it on Canvas. So you will have the links. All right. Well, have a good evening. Good afternoon. It's still light out for a while longer. Although first day of fall, I guess. All right, have a good one.